Good morning, boys and girls. This is Mrs. Erwin at Robey Elementary. I'm here with Mr. Crosslin today, and we're going to be talking about gravity and inertia and answering the question, how do gravity and inertia help to keep objects in motion?
Hey, thanks for that great introduction. So today's lesson, I'm kind of excited about because it has some complicated things in it, and it's about gravity and motion. We all experience gravity and motion, but it's also about space. And so when you talk and learn about space, it's hard to go to the moon. It's hard to visit another planet. So I kind of go back and forth with this. I want to do some things that maybe you can experience about gravity and motion. So some of the words we're going to study today are gravity, and another word is, of course, mass, and another word I want you to know the difference, and this is a big one, weight, and finally, the word inertia. Inertia. So these are some of our key words that at the end of this lesson, I hope you have a better understanding of them about how things move and go. But I got to tell you something. I just came back on a trip to England, and I had the opportunity to visit a lot of places about science. You see, England has some amazing past history of science and present history of science. And so I'm going to try to tell you a little story today about motion and gravity and England. One of the places I visited in England was a place called Cambridge University. Have you heard of Cambridge University? Cambridge, the town, it has about 30 different colleges at it. And it's the kind of place where people have been going, some of the smartest people in the world have been going there for hundreds of years. It kind of reminded me a little bit of Harry Potter, some of the buildings and things. So I went there because people like Charles Darwin went to school there, and people like Sedgwick, who is a geologist, and Charles Lyell, and the person we're going to talk about today also went there. But before I tell you about this guy, I got to tell you something. He was born back in the 1600s. You may know who he is. That was a long time ago, over 350 years ago. And he was born on Christmas Day. Now, back then, if you were rich or your parents were influential, you could go to Cambridge. But he was born on a farm. And I got the chance to visit there. In fact, I got on a train, and I got on the wrong train first. I had to get off it. And I ended up in a place called Grantham. And I got off the train station, and I found a taxi. I said, I want to go out in the country to a place called Woolsthorpe Manor. And the taxi driver scratched his head. Why would an American come all the way, 10-hour flight, land in London, 2-hour train ride to go to a farmhouse in the middle of nowhere? I said, no, that's where I want to go. So I pull up to this place, and this place is where a man that was born. It was kind of a cool story because his father died 2 months before he was born. And when he was, his mother, Emma, did not know for sure if it was going to be a boy or a girl. Now you might say, well, why is that important? I'll tell you why. Because back in the 1600s, to own land, it had to be the father or the son. And since the father had died, if a girl had been born then, they would have lost all their land. So she was quite happy to know that her baby, her first baby, was a son. Bad for the boy because his father had died. Well, he was supposed to grow up and inherit the farm and be a farmer. But there was something different about this young man. First of all, he scratched pictures and drawings all over the walls of the house. I mean, not just like pictures like I would draw, you would draw, you know, like cats and dogs, but of big churches and bridges. So he had an eye for math and an eye for science. Now, instead of being a farmer, someone noticed that he was really smart and said, we should send this young lad to Cambridge. So off he goes to Cambridge. Now you're thinking, what does this have to do with gravity and inertia? I'll get to that in just a moment. So off to Cambridge he goes. Now, something terrible happened in England during that time. It was called the plague, or the Black Plague. People were afflicted with this disease, with spots, and they would die. In fact, in this room, I hate to say it, but if the plague hit this room, 2/3 of you would be dead. And people would come through the village with their carts, bring us your dead, bring us your dead. And out would come families or children or parents, piled on carts, taken to the edge of town and burned. They really didn't know what was causing this plague. We know now that it was fleas. People were kind of like dogs have fleas today. Well, people have always had fleas too. And back in the 1600s, you didn't know about germs. You didn't know about taking baths or washing your hands. In fact, people wore like a body stocking for months at a time, maybe a bath once a year. So you had your friends with you, your fleas with you. And inside of these fleas, they carried a disease called the plague. And when a flea would bite you, you would get the plague. And so many people were dying that this person thought, you know, I should leave Cambridge and go back to my home in Woolsthorpe Manor, and wait it out. Let me show you what his home looks like. So this is a picture of that countryside manor house. And it's pretty old, and it's well kept. It's like a little museum now. So I ended up going here and walking through there, and if you look, this was his bedroom right here. And out the side is a window right here. And so this guy spent 1 year there while the rest of the country had the plague, okay? And it was called the Year of Wonder. One of the things he did was he took a prism, and so you kind of see the light coming right here, and he studied light coming in through this window, and using a prism, he could split the light into a rainbow. That was his first discovery. In fact, people have not thought about that before. If you know what I mean, look, see my glasses right here? Can you see how there's, I don't know if you can see the
rainbow.
The rainbow, you know, that he kind of worked out, and of course that's not a prism, but there you got to see a little bit of it. So that is something that he worked out. And as the year went on, his next big idea has to do with this next picture right here. You know who that is, right? So, anybody know what I'm standing in front of? Yes, what?
A tree.
A tree, right?
Oh.
But what kind of a tree? Let's arrow down one more picture, and I'll tell you. In fact, what tree? An apple tree. Would you turn the lights on? And who am I talking about? Anybody know? Say it.
Sir Isaac Newton.
Sir Isaac Newton. In fact, I'm going to show you something about Sir Isaac Newton and this apple right here. Okay, so this is an apple from that tree, from Isaac Newton's tree. Or we should say Sir Isaac Newton, because of how important he was knighted by the King of England. Now he's Sir Isaac Newton. Now check this out. Here's what he did. And I'm going to pass this around to you because it's not every day you get to hold an apple that came. Now, mind you, the tree was 300 years ago, and the tree actually was knocked down in a storm in the 1880s, but it didn't die. The roots grew, and the people have kept the tree growing. So this is a great grandbaby from that tree. You see, I did this very same experiment. I picked this apple, and I let go of it, and it did something amazing. It
Fell.
It went down. It fell to the center of the earth. In fact, Isaac Newton ended up writing a book about the laws of motion. And he started with this apple. The story goes like this. He said, after tea, I was walking in my garden, and I happened upon an apple falling from a tree. And I thought, why does the apple fall down perpendicular to the earth? Why doesn't the apple go sideways? Why doesn't the apple fall up? But no, there's something that draws it to the earth. And that something that draws it to the earth is gravity or gravitational force. And so he thought maybe all things move a certain way. And he sat down and he wrote the laws of motion. And there's 3 of them. Would you guys like to see them? Here we go. So I'm going to pass this around so you can hold and drop an apple from Isaac Newton's tree. Boys and girls, you don't usually hear the word laws in science. I'll tell you why. If it's a law, it's supposed to work all the time. Now you might have an idea in science and test it, right? And if you test it 100 times, you might collect data and think, oh, this is a great theory. And the theory might change. But if it's a law, it's supposed to happen all the time. Got that? So his first law, law number 1, was really the law of inertia. Some people call it the law of inertia, which means, are you ready for this? An object in motion continues in a straight line or a straight path until a force acts upon it. Now that's a lot. Got it? Inertia. An object in motion continues in a straight path until a force acts upon it, and an object at rest stays at rest unless there's a force. Got it? Hey, let's take a look at law 1 and what that looks like on your desk. All right, so here's our first law. Are you ready?
Ready.
So if Isaac Newton is correct, if I throw this soft ball towards you, it should go in a straight line and keep going in a straight line forever, right?
No.
Well, unless a force acts upon it, right? So watch the path and tell me. Let's see, ready? I'm gonna throw it, it should be in a straight line. Was that a straight line?
No.
Are you sure? Well, throw it back to me and see. Was that a straight line?
That was a rainbow.
A rainbow.
Like a rainbow line.
Now I know Isaac Newton studied light and he broke light into a rainbow, so I appreciate you saying it's a rainbow. In fact, this is called a Newton's wheel. When he split that light into the colors, he thought, what if I put all the colors and I spin them, can I make it go back to gray or white light? You see how it goes all together? So I like that you said rainbow. This is called a Newton's wheel, by the way. But maybe you kids are not observing good. He said it's going to go in a straight line. Well, unless what? So this is not a straight line. I'm going to try it one more time. Everybody look. Straight line? Yes, yes?
No.
How did it go? Like kind of like that?
Yes.
A rainbow?
No, it didn't.
Well, why did it go like that? Why? Yes. What force?
Gravity. Gravity's pulling it down.
Oh, so I pushed it forward, but gravity's pulling it down. So show me again. You see it kind of go like that?
Yes.
Now, what if I be careful. What if I increase the acceleration? See if I'm gonna go a little bit faster. See if it's a straight line. Are you ready?
No. Almost.
Almost. A little bit faster. What about now? What about now? Ready?
Yeah, it was straight.
So if you increase, but oh. So let me show you about here. Let's say this is the Earth, right? Well, it's kind of like a lemon, but there's the Earth, right? And here's the center of the Earth. And just like I showed you that apple tree with Isaac Newton, where's the apple at? Just like I showed you that apple that falls straight down, Isaac Newton, he came up with this idea. What happens if we do this? Let's say we take a cannon right here, a big cannon, right? And we shoot a cannonball out of it. No, just a cannonball. Is it going to go in a straight line?
No.
What's going to cause it to fall? Yes.
Gravity.
The gravity. So it'll go like this. Yeah, you know. But what if you shoot it faster? Ready? Now, do you see where I'm going with this? What if you shoot the cannonball even faster with more force? Can you see where I'm getting at? And this is why Isaac Newton helped us go into space and explore the moon and Mars. I'm going to show you why. Because if you can make this ball go fast enough, ready? it will go completely around the earth. Think about it. So if I throw this ball hard enough, I don't know if I can, but if I can accelerate this ball, if it's slow, it's going to do what? Curve down, right? Here we go, let's see. It curves down. But if I can throw it fast enough, here, why don't you come here and throw it fast enough for me? I want you to throw it to the back of the room so fast that it goes all the way around the earth. Be careful, it'll come and hit you in the back of the head.
Yo!
Oh, wait a minute, a force got in the way, didn't it? Here, throw it back up here. Let's try one more. Ready? Here, stay right there. Let's see. I want you to just throw it towards the camera, slowly at the camera, and let's see what happens. Slow. Ready? Did it go straight? Why didn't it go straight? Gravity pulled it down, but what other force? Do it again. What other force caused the motion to change? What? Yes. Yeah, come help me. Maybe you can do this. Ready? You stand right there, and you're going to try to make it go in a straight line. It won't because of gravity pulling it down. And what's your name? Malia. You see if you can interrupt the path. Get your hand ready. Throw it slow so she can get it. Oh, that made the motion go completely in a different direction. Let's take a look at the second part of his Law 1. The second part of Law 1 says an object at rest will stay at rest unless a force acts upon it. That means that this cup and this spoon should stay here forever unless you knock it over or something. And let's see if that's true. Wouldn't it be weird if on Thursdays his law was wrong and every Thursday everything fell up? Every Thursday that you wake up at 2 o'clock, everything went sideways? Wouldn't that be a strange world to live in?
Yeah.
That's why it's a law. Laws usually don't change, and I'm kind of happy about this one. So if I do this right, this is inertia. An object at rest stays at rest. Oh my goodness, this is nervous. Okay. But if I do it, guess who's going to do it next?
Not me.
There we go. Ready? Move your arms back. Oh, I hate this part. On the count of 3, say inertia. 1, 2, 3. Oh, I gotta try it again. That was supposed to stay at rest. I think it bumped. Let me turn it like that. Let's try it like that. Ready? What do you think? What do you think? You're not gonna do it? Don't be so negative. On the count of 3, say inertia. 1, 2, 3.
Inertia!
Whoa! Miss Erwin, so you have to hold and pull down tight and don't hurt yourself.
Okay.
And what does this law say? An object what?
In motion stays in motion unless acted on by an outside force.
And an object?
At rest stays at rest unless
Okay.
acted by an outside force.
So pull hard and down. On the count of 3, everybody say inertia. Breathe. You're going to pass out. 1, 2, 3. Inertia! Yes! Nice job. And that is Law 1. So that was Law 1. Law 2, it can be kind of complicated, but really I'm going to use a formula. Law 2 means force equals mass times acceleration. What? What he thought was the force of something has to do with how much stuff it has in it and how fast it's moving. Got that? So a force is equal to how big something is and how fast it's moving. Let me give you an example. Let's say you have a driveway like this or an inclined plane, right? And you have a skateboard. It's rolling down the hill at 5 miles an hour. Could you stop that skateboard with your hand or foot? Yes? Probably pretty easy to do. What if you have a car? This is my best I can do on my car this morning. There's a car, and this car is also going 5 miles an hour down the road, down the hill. Could you stop it?
No.
With your hand?
No.
A car rolling 5 miles an hour, you cannot stop because it weighs thousands of pounds. And so this explains that even though they're going at the same speed, this one has more mass than this, and it has more force. All right, so let's show that. Let's take a closer look. Okay, so here's my friend Destin, and you notice that I'm a little bit big. Sorry, I'm a little bit bigger than you, right? I've been eating a little more maybe. and but you're a pretty good size, right? You speak? You say anything?
Yes.
Okay, good. All right, so this is a good example of what mass is. So you see, I have more stuff in me than he does, okay? So I have more mass. So our mass is different. Let's say that I am 100 kilos, and you're probably 30 kilos. Now, if we got on a spaceship and we went to the moon, guess what? You would still be 30 kilos, and I would still be 100 kilos. Your mass does not change. You got that? Your mass is how much stuff you have in you. Now, if I chopped off your arm, I wouldn't want to do that, you would have less mass. Get it? We're not going to do that. But here's what's different with weight. Weight, on Earth, I weigh about 200 pounds. You probably weigh about 60 pounds. But on the moon, maybe 65, I don't know. On the moon, since the moon is smaller than the Earth, 1/6 the size, if you weighed 60 pounds on Earth, you'd only weigh 10 pounds because weight is a measure of gravity compared to you and the object you're on. So on the Earth, Destin weighs 60 pounds. On the moon, it only weighs 10 pounds, which is also kind of cool, which means on Earth, come over here, let's see how high you can jump. On the count of 3, squat down and jump. 1, squat down. 1, 2, 3, jump. Wow, about that far. On the moon, you could jump 6 times taller. That'd be kind of cool to do. In fact, when the astronauts went to the moon, one guy famously hit a golf ball hundreds of yards. Cool. But here's the thing. Our mass doesn't change, but our weight does. So weight is a measure of the gravity force. Mass is how much stuff you have in you. Got it? Got it. All right. Oh, don't go to Jupiter. If you could go to Jupiter, like the Juno probe that just landed there, maybe you heard about it on the news. It took 10 years to get there. And we're going to talk about it. Remind me of that because I want to show you something. If you could get close to Jupiter and stand on Jupiter, it is so big that the minute you tried to stand up, the gravity of Jupiter would pull you down, break your legs, squish you into a pancake, and you'd be dead. Because it is so much bigger. I don't know if you know this, kids. Check this out. Here's one thing I'd like you to know. Here, if the sun is this big, put your hand down, Dustin. If the sun is this big, the Earth is only the size of this cap. Hold that cap. If the sun is as big as Destin, the Earth is only as big as this cap. So let me ask you this. Who has more gravity? The sun or the Earth? The sun. Even though on Earth everything falls, it's the sun that holds it together. Now Jupiter would be about the size of my fist compared to the sun and the Earth. Maybe a little bit bigger. So who has more gravity, the Earth or Jupiter?
Jupiter.
Jupiter. Thanks. Now here we go. Let's do law number 2. Are you ready? Put your hands down. Now, so law number 2 says that there's going to be a bigger force because I have more mass than Destin. So here's what we're going to do. We're going to do this slow motion like Matrix style, right? You and I are going to run up and belly bounce, okay?
Oh my God.
You done that before?
Nope.
Well, what do you think's going to happen when let's go slow motion. We come together, slow motion, Matrix style. Boom. What do you think's going to happen? Who's going to go flying and who's not going to go flying? Why will he go flying when we're both coming together at the same speed? Say it again.
You have more mass.
How rude. I have more mass. Now, all right, so here we go. Ready? Slow motion, because I don't want to hurt anybody, especially me. We're going to go like 2 miles an hour. We're going to belly bounce, and something's going to happen to him, I hope. Here we go. Law 2. Here we go. Now, what did you notice? That was so cool. What did you notice? When we collided, he went back farther, but did you see that I went back a little bit? That was kind of cool. This time, let's do it fast motion. Okay. Oh my gosh. There we go. Ready?
Oh no.
It's going to hurt me more than you, I think. 1, 2, 3. Law 2. Boom. Oh, did you see what he did? Did you see what he did? He increased his speed and knocked me back. Did you see that? Bad boy. No, that was smart. See, you can increase the force by 2 ways. Getting more mass or more speed. For example, watch this. Stand right there. come a little bit closer. I'm going to throw this ball and knock him back. Ready?
Good luck.
Let's see your chest there, man. Make some muscle. You're killing me. Here we go. Ready? He didn't go backwards. But guess what? If I throw this ball 1,000 miles an hour, even though this ball doesn't have much mass, if I increase the speed, bam, it would actually probably knock him through the wall. In fact, let me show you something right here. I saw a study on the space shuttle, you know, the space station, the space shuttle in NASA. It's going over 1,000 miles an hour orbiting the Earth. It's actually falling. Most kids think that there's no gravity in space. Most people do. But actually the space station and the space shuttle is going so fast that it's trying to fall into the Earth, but they keep boosting it so it doesn't. So it's going thousands of miles an hour. They brought back the space shuttle and they looked at the window in it and there was a big crater in it. I thought, what hit it? Was it a giant rock? Was it a meteorite? No. It was a flake of paint. A piece of paint, flake of paint, that was traveling 3,000 miles an hour, hit the space shuttle window. Now, you see how that works? Even though it has little mass, it was accelerating really fast and made a big force. Got it? Let's try one more thing to show you this. Explain what we're going to do.
They're going to push their feet together, then Destin's going to go flying back, and we're going to see how far he flies back.
Who do you think will fly the most?
Destin.
Why?
Because he weighs almost 60 pounds.
And he has less mass. Let's see if you're right. 1, 2, 3, push. Whoa! Now the cool thing about that was he went back a lot, but I also went back some. And this brings us to the third law. And the third law is for every action, there's an opposite and equal reaction. All right, let's try one more time. Let's see the action. This time, you don't push, I'll do the pushing, okay? So that's going to be the action. And what's going to be the reaction? He's going to go backwards, and I'm going to go backwards a little bit. 1, 2, 3. And you see I moved a little bit. Let's try it one more time. You push also. Don't hurt yourself or me. Here we go. 1, 2, 3. And that is Isaac Newton's laws of motion. Okay, and so the third law, which we've demonstrated, for every action, there is an equal and opposite reaction. Okay, so let's tie this all together, literally. So here is a ball that's going to represent the Earth. Got it? My fist is going to represent the sun. In fact, write the word S-U-N on there for me, okay? Sun. So this is the Earth, S-U-N. Sun, got it? So, this is a model. When scientists use models, they're not exactly alike the real thing, but they help us learn about the real thing. So science models, like all models, have limitations. All right, so you learned last week, I hope you get this right, when an object is spinning like this, that motion is called rotation. And when an object is going around something, revolution or an orbit, right? This is what? Rotation. Good night, good morning. Good night, good morning. And this is revolution. Happy birthday, you're one. Let's put that together, right? So here's my model. There's the Earth. What is my hand?
Sun.
The sun. And this is revolution. This is orbiting the Earth, right? So, what does the blue string represent? What? What? Say it. Gravity. So here's my big question. The $10,000 question. Is there gravity in outer space?
No.
Yes.
You said no?
Yes.
Bad girl.
Yes.
Here's what happens if there's no gravity in outer space. Are you ready? If there's no gravity, there's no string.
Oh.
Sorry, I had to demonstrate that. Go get the Earth for us. So, if there was no gravity right here, you got that? This is what would happen. The Earth would do what Isaac Newton said. It would just continue in a straight line. But because of gravity, it wants to move, but the Earth pulls it together. Now, I hate to tell you this, kids, You don't have to wait up for it. But in billions of years, this is what's going to happen. The Earth's gravity, or the sun's gravity, is going to do this and pull it right in. Don't worry about it. The star will probably go supernova later anyway. What happens if it's far away from the sun? Look at the speed. What do you notice? A bigger circumference, and it goes faster or slower? What do you think? Slower. Watch what happens if I decrease the radius. Ready? What is it about the revolutions you noticed? Faster. And so, if you get on Jeopardy or Who Wants to Be a Millionaire, phone a friend. Call Mrs. Erwin or Mr. Crosslin, because if they ask you, is there gravity in outer space? You will say,
Yes.
yes. In fact, that's what holds the planets together. And because of this, Isaac Newton was able to come up with a new kind of math called calculus that measures unknown variables. And because of that, we have been able to travel to the moon and to Mars and beyond. So you don't want to be that planet that does not have gravity. So gravity can also be used to change your direction. Have you guys ever heard of this program here from NASA called the Apollo space program?
Yeah.
Their job was to do what? Go where?
To the moon.
To the moon. And I remember, I was a little young, I remember on July 20th, 1969, sitting in my grandfather's front room, watching a black and white television where Neil Armstrong, a Purdue graduate from here in Indiana, stepped out of the lunar lander, and what did he say? Who knows the famous words he said? What did he say?
This is one step for man, and this is one leap for humanity.
Exactly. That's one small step for a man, one giant leap for mankind. First time we went to the moon. Now, I don't know if you know this, but here's the moon, and here's the Earth. It takes like 3 days to get there. So the rocket, like a Robey rocket, takes off, starts going around the Earth faster and faster, and then it coasts motion all the way to the moon, goes around the moon, because the moon is actually moving also, and then comes back. It took them 3 days to get there, 3 days back. Now, the other thing that's kind of cool is if this was the rocket to scale, it takes so much energy to lift off the Earth to overcome inertia, because things want to stay at rest, that as it goes up and starts going around the Earth, this much of the rocket is done. And this rocket, the Saturn IV rocket, was as long as Robey, maybe even bigger. So in the first couple minutes, it uses all this, and the cap is what's heading to the moon, coasting. So, and then silent in space. 237,000 miles, 3 days. 3 men inside of it. They get to the moon. They start orbiting the moon. One man stays behind in the command module and orbits and goes around while 2 land on the moon. How would you like to be that one man who was in that command module by himself, the loneliest man in humanity? Because he was the farthest from Earth, and when he goes on the backside of the moon, he couldn't even use his radio. That would be something. I'd like to do it.
No.
The other 2 guys walk around, get back on, come back to Earth, fire their rocket, coast for 3 days, get close to the Earth, turn the rocket around, try to slow down, and splash down in the ocean using motion. But here's something cool. Apollo 11, excellent. The Eagle has landed. Apollo 12, excellent. Everybody was excited. And then came, I want you to look this up in your Chromebooks, Apollo 13, which I say may be the coolest, courageous mission of all. Does anybody know what happened in Apollo 13? Same thing. They take off, use up all the fuel, around the Earth, and they're headed to the moon. Right about here, half of the spaceship blows apart. An oxygen tank blows up. They turn the switch to heat it up, to stir it, a spark. The spaceship's out of control. They had like 2 hours before they used up all their energy. They're in big trouble on their way to the moon with nobody to help them, and they call back to Houston, and they famously say, what did they say on the radio?
Houston, we have a problem.
Say it louder.
Houston, we have a problem.
Houston, we have a problem. And boy, did they have a science problem. They're going thousands of miles an hour like this, and are going to do, three things are going to happen. They're going to hit the moon and die. They're going to miss the moon and be gone, or they can make it back to Earth. Okay, so we're going to reenact what's called the Slingshot gravity assist that happened in Apollo 13, right? Apollo 13, you're Apollo 13. Okay. You're on your way to the moon. I'm the moon way over here. And what happened to the moon, it's doing its thing. It has gravity. You get halfway here, come halfway here, stop. You have a big explosion. That arm goes flying up, and now it goes down. You explode on the way, and you say some famous words. What do you say to Houston? Turn around to the camera and tell them.
Houston, we got a problem.
Houston, we got a problem. So they have to figure out, because if you turn around, and you come walk towards me backwards, and you try to fire your rockets, you'll get about this far, and then you'll start going that way, and then stop. You'll run out of fuel. You'll never make it back to Earth. So here's what we're going to do. Turn back around. Start over again. The Apollo 13 takes off, comes a little bit. Let's blow up that arm this time. Hook that one, hook that arm. What do you say?
Houston, we have a problem.
But here's how we're going to solve this problem. We're going to use the moon's gravity to slingshot you. So here's what happens if you miss the moon. Go right on past me. And the moon pulls a little bit. He's lost in space. That dude's gone. Oh, eventually he'll come back. The sun will pull him back, but they'll be dead by then. Let's try it again. This time, I want you to go as fast as you can. Hook your arm hard. Stop right there. Hook that arm hard. That one right there. Hook it hard. You're going to shoot by me. I'm going to pull you into me and see if I can slingshot you back. Ready? Go. Fast, 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 fast. Bam! We just saved Apollo 13. I used the moon's gravity to slingshot. See how you got even faster? That made you go faster. And that, my friend, is called gravity assist. Thank you very much. This is going to be a spacecraft. And this magnet, a very strong magnet, is going to be like the moon with gravity, right? So remember my friend Apollo 13? If we miss it, we go past it. That didn't miss it though, did it? If we go past it like this, lost forever in space, okay? If we go too close to it like this, crash. End of the Apollo. But what if we could get, and this is hard for me to do, but maybe you can do it. Let me put this underneath here. I don't want to go too much because that'd be too much acceleration. But if I put it just right, see if you can see this thing, because Isaac Newton said that's not going in a straight line. Did it go in a straight line? No. Watch this. Did you see what it did? Did you see it curve? Way over here, straight line, right? If you do it just right, I don't know what that is. You're going to have to figure it out. 3. What do you think? Right there. I made some marks. What do you think? Try this side. Let's see if we can get it to curve. Nope. Nope. Oh, there was a curve. See the curve? Mm-hmm. When you read about this in your book, I want you to remember this demonstration. You're going to have to figure this out. I'm going to get you some time to practice, and you guys will see if you can do it. Did you see it curve just then? Try it again. Very cool. One more time. I think you guys got that down. You guys want to try it?
Can you go place that the magnetic force?
I did it!
That almost went all the way around it, didn't it?
I know, I'm trying to do that.
You just lost in space, man.
I know. I am Riley, I'm the videographer, and I learned a lot about Isaac Newton.